Okay. So for the rest of this semester, we only have 2 chapters left, right? We have chapter 7 and chapter 8. So basically these 2 chapters are very straightforward, and they're much simpler than chapter 5 and chapter 6. So probably we'll spend just 1 week for each chapter. And for the rest of the semester, we're going to talk about statistical thermodynamics more. Okay. So chapter 7 is about the phase equilibrium, or you can say the phase diagram for a one-component system. And typically when we talk about one-component system, the most intuitive example will be water. So if we're using H2O as an example, people typically know, like for instance, the melting temperature is 0 degrees Celsius, the boiling point is 100 degrees Celsius. So you have a basic knowledge of what we're talking about. So typically when we talk about one component system, we'll start from the system of a bunch of water or water molecules. But essentially for this chapter, the most important concepts are these 2 equations. So we're going to talk about the phase equilibrium using the concept of Gibbs free energy, which we learned in chapter 5. And Gibbs free energy, or a slightly change of Gibbs energy, which is represented by dG, is the combination of minus SdT plus VdP. So we're going to see what will be the change of Gibbs free energy when you change, for instance, temperature, and when you change the pressure. And also, when you have different species in your material systems, for instance, if you are dealing with more than one component, then you have to worry about chemical potentials from different material species. Okay, so basically, Gibbs free energy will be changed by tuning the temperature and by tuning the pressure. And from this equation, you can also see that the rate of change in terms of Gibbs free energy with respect to temperature is related to entropy. So partial G partial T will be minus S. Okay, so if you know some basic information, or if you have the basic knowledge of entropy of some material system, then you can sort of try to figure out dG over dt by using this equation. And that will be the same for dG over dP. So when you change a little bit of your pressure, and the Gibbs free energy will also change a little bit, and the rate of that change will be related to the volume, or you can say the molar volume of the material system. And so the concept for chemical potential, or chemical, or say the molar Gibbs free energy, will be the same. Recall that from chapter 5, we learned that this chemical potential for a specific species will be related to partial G and over partial N. Okay? And we tried to prove this in chapter 5. So these are the concepts that will be used in this chapter. So sort of an introduction. This is similar to what your textbook has. For this chapter, when you're dealing with a phase diagram, typically you will use several different intensive thermodynamic properties as your axis to plot out your phase diagram. And 2 of them are the most common ones, for instance, temperature and pressure. So that's the reason why we talk about temperature first. Temperature is, again, an intensive thermodynamic property, so it does not depend on the size of your system. So it's a good macroscopic measure. Okay? So temperature is a measure of the potential, or you can say the intensity of heat in the system. And it is also a measure of the tendency for heat to leave the system. So if the temperature is higher for your system, so it's more likely that the heat will be dissipate, from this system to outside, right? So that's our basic concept or basic understanding of what temperature is. And at the very beginning of this semester, we talk about thermal equilibrium. So thermal equilibrium is established when the heat potential, therefore the temperature, are uniform, throughout the system. So when the temperature of two systems are the same, then it means that they are in thermal equilibrium. There will be no heat transfer between these two systems. That's what we learned when we talk about the 0th law of thermodynamics. Okay, so that's basically a review of what temperature is. And the other intensive property will be pressure. Okay, pressure is a measure of its potential, or you can say mechanical potential, for undergoing massive movement by expansion or contraction. Consider you have a volume of gas molecules. Then the pressure, if you increase the pressure, then you are compressing those molecules to become with a smaller volume. So you're basically moving the molecules towards some certain direction. And therefore, the pressure gradient will be the driving force of this expansion or contraction. And similar to temperature, if we want to use a same analogy, then the pressure is a measure of mechanical equilibrium. So consider temperature is a measure of thermal equilibrium. Then the pressure will be the measure for mechanical equilibrium. So therefore, mechanical equilibrium is established when the pressure gradient has been eliminated, which means that, for instance, if you're dealing with two systems, those two systems are in mechanical equilibrium when the pressure from both sides are the same. Okay? So in that sense, the state of the pressure is uniform throughout the system. Okay? So this is just a quick review of pressure. But what we learned in chapter 5, is that we also have this chemical potential, which is related to the molar Gibbs free energy of some certain species. And typically we say that it's mu I, and also this mu I is related to the Gibbs free energy over this size of the species I. So if you're dealing with the chemical potential of a certain species I in your material system, then it can also be expressed as the rate of change of Gibbs free energy when you change the amount of molecules in that species, okay, or in that phase, or in that component. Therefore, you can say it's the molar change of Gibbs free energy for this certain species. Okay. So mu I is a measure for the tendency of species I to leave the phase. For instance, if mu I is higher, for instance, if you have consider you have two species in your material and it has a certain phase boundary, and if mu1 is greater than mu2, then we know that the molecules in species 1 will tend to move to this phase 2 or species 2, right? Because the chemical potential describes the tendency of that certain species to leave that system. Okay? So if mu1 is greater than mu2, then it means that these particles are having a trend to move to the other side. Okay. And therefore, mu I is a measure of the chemical pressure exerted by I in the phase. So it means that if you have mu1 greater than mu2, then the particles will start to move from this side to this side, and then eventually, when in equilibrium, then mu1 should be the same as mu2. Okay? And that is related to the relative numbers of particles on both sides. So at the beginning, maybe you have more particles over here, so you have N1, also N1 greater than N2, but eventually, depends on your chemical potential. Maybe you'll have N1 less than N2 eventually. And then you have mu1 equals to mu2. And that is when the equilibrium is reached. Actually, we won't talk a lot about these for this semester, but for next semester, when you are taking the second half of thermodynamics, I believe that you will encounter more of these kind of things, because for the next semester, you're going to learn more about phase diagrams. But at least in this chapter, we won't see a lot of expressions or derivations that is related to chemical potential, because again, for this chapter, chapter 7, we're dealing with one component system. So typically, we will just focus on pressure and temperature as our measure of thermal equilibrium. Okay. But of course, if you are dealing with constant pressure and constant temperature, but the species, the numbers of particles in different species or different phases in these materials are different, then the chemical potential will be the measure of the movement of these particles or these molecules. And therefore, the species I will tend to move from the phases in which it occurs at higher chemical potential to a lower chemical potential. Okay, that's just what I described over here. So a gradient in chemical potential will be the driving force for chemical diffusion. Okay, and when the system is reaching the equilibrium, it means that the species I distributed throughout the various phases in the system, when the chemical potential are having the same values throughout the phases. Okay, so when mu1 is the same as mu2, and it means that the system is in equilibrium. Okay. But again, in this chapter, we won't talk more about this. We'll go back to, we'll switch our focus back to the pressure and the temperature and how it will change the Gibbs free energy. So therefore, starting from the next section, we're going to look at Gibbs free energy as a function of temperature at constant pressure. So we already know that typically Gibbs free energy as a function of temperature and pressure, right? Because if you recall that dG is minus dt plus dP. If you ignore the chemical potential part, like what we're dealing with in this chapter, because one component system, typically we only need to focus on just one species of materials. So we only have these two variables, which is temperature and pressure. And for the first scenario, we're going to look at the case of constant pressure. So dP is 0. So if we don't have this term, then the change of Gibbs free energy will be only related to temperature. So that's the reason why in this case, Gibbs free energy will be a function of temperature only. Okay? And so the simplest material system, like I mentioned earlier, will be water, because we know what water should act at room temperature and also at normal conditions. So if we look at the simple melting process, okay, you have H2O, and originally, for instance, it's in the solid phase, it's an ice, and then it will be melted into water in the liquid phase. And if we're looking at this kind of process at 1 atm, which is the normal pressure, atmospheric pressure, and at 273 Kelvin, which means that you're dealing with this kind of process at 0 degrees Celsius. Then we know that ice and water can coexist. Therefore, the Gibbs free energy, or the delta G for this process, should be 0, right? Because you can have all of the water molecules as ice, or you can have all the water molecules as liquids, as water. So being liquid, H2O, or solid H2O, should have the same Gibbs free energy at this condition, right? When you're dealing with a constant, at normal atmospheric pressure and at 0 degrees Celsius, we know that these two phases of water should coexist. So if you consider that as a chemical reaction, then the Gibbs free energy from the evolution from here to here should be 0, should have a delta G of 0. Then it means that for water and for ice, they should have the same Gibbs free energy, right? If you consider them as two different species, then they should have the same Gibbs free energy. But of course, they are the same. They are the same species, but they're in two different phases. So this is very important, especially if you want to express your Gibbs free energy as the total of from the contribution of water and the contribution from the ice. And we know that the total molecule numbers will be a constant, but you have a part of them being solid, being ice, and a part of them being liquid. So the total Gibbs free energy will be the sum of all these two components. And the G prime states here is the Gibbs free energy of the system containing n moles of H2O, and n equals to the sum of these two, right? Both ice and water are made of water molecules, or H2O. So in this case, the moles of ice and water, these two, if you add them up, it should be the total numbers of, or total mole numbers of H2O. So this is the way to write down a single species material with two different phases as a component, as a two-component system, So at 0 degrees Celsius and the normal pressure, the value of G prime, this total Gibbs free energy, should be independent of the proportion of ice phase and water phase present. So this is like what I mentioned earlier, because from the equation we saw over here, the Gibbs free energy for liquid phase and for solid phase are the same. So which means that these two are the same number. I mean, the solid and liquid phase Gibbs free energy should be the same number. So, and we know that this, when you add these up, this is a constant. So it means that G prime should be independent of the proportions of ice and water phase present. So this means that here we're dealing with G prime is the total Gibbs free energy. I would just say ice water and we know that at 273 Kelvin, which is 0 degrees Celsius, and of course 1 atmospheric pressure, this is the melting point of water, right? So these two things, water and ice should coexist. So G ice should be the same as G water. Therefore, the total should be, you can say this is G ice because these two are the same, only at this condition. So if your pressure and temperature, one of them or both of them are deviated from this condition, then this derivation will not hold, right? This is only when the system is at equilibrium. You can write this. You can simplify this right-hand side as this. And since we know this is also a constant, this is just n. Or you can say n total. So this is a constant. So if you have 1 mole of ice and 99 moles of water, and if you have 2 moles of ice, then you only have 98 moles of water, right? And these two should add up as a constant. And therefore, this number is a constant. And we know that this is also a constant at the fixed temperature and fixed pressure. Therefore, this is independent of the relative numbers of ice and water in this system. So you can have a lot of ice and only a small bit of water. You can also have a lot of water molecules, but only a small bunch of water in the solid phase. Okay, so this is what this section is about. And for equilibrium at this normal condition, the escaping tendency of H2O from the liquid phase to the solid phase will be the same for the reverse process. So in this case, we know that if you want to plot it schematically, we know that we have ice, we have water, and the tendency of ice leaving, or water molecules leaving ice phase and goes into the water phase should be the same as the tendency of water flowing into, or leaving water phase and going into ice. And in this scenario, we know that mu ice should be the same as mu water, if you want to consider them as two different species. Then you can express the chemical potential of ice as the same as the chemical potential of water, because at 273 Kelvin, 1 atm, this is the case. But that won't be the case if you raise the temperature, right? So if your temperature is, say, 298 Kelvin, 25 degrees Celsius, we know that water in equilibrium, water is the stable phase. So ice should not exist. Although at the very beginning, maybe you can have ice water, but eventually you know that ice is going to be melted. Therefore, if you're dealing with 298 Kelvin, then you know that the stable phase should be just water only. So if you suddenly raise the temperature, for instance, to 298 or 300 Kelvin, then you know that the chemical potential for these two species will be changed. In that sense, so if you raise the temperature, let's just write over here. So if temperature is greater than 273 Kelvin, then this then this chemical potential of ice should be greater than that of water, right? Because we know that when you raise the temperature, water will become the stable state. Therefore, the molecules originally in the ice phase will leave this phase and become water. Therefore, if you raise the temperature, you know that the chemical potential of ice should be becoming higher than that for the water phase. So that's just the basic concept of using chemical potential to describe this kind of phase changing behavior. So again, recall that the total Gibbs free energy is the sum of the ice and the water. Sorry, I think I erased that. Oh, maybe it's over here. So recall that we have this kind of expression of the total Gibbs free energy. And in a state of equilibrium, we know that the Gibbs free energy should be the same. And over here, we also describe this as a chemical potential. Therefore, I think we derived this in chapter 5, that we know that this Gibbs free energy that we described for each species is essentially the same as its chemical potential. Right? Okay, so when we're talking about mu ice equals to mu water, it simply means that the Gibbs free energy for ice, or the molar Gibbs free energy of ice, is the same as the molar Gibbs free energy of water. Okay, so you can use these two terms interchangeably because they are the same. They are the same. So the chemical potential of a species in a particular state equals to the molar Gibbs free energy of the species in that particular state. And that's what we derived, I think, in chapter 5. So again, if you look at the original definition of chemical potential, it is actually partial G prime. The total energy, the total Gibbs free energy, it can be represented as a function of N ice and N water. And if you take partial G, partial N ice, then this is the thing that you will get, right? You'll get mu ice. So partial G prime, partial Ni will give you the chemical potential of species I. Okay, this is from chapter 5. And in the one component system, the chemical potential of the component equals to the increase of the value of this G prime over here. I believe if you use the version on Seba, I think I corrected this. This is in the value of G prime, of which occurs when 1 mole of the component is added to the system at constant pressure and constant temperature. So it means that this mu I represents the change of total Gibbs free energy when you add 1 mole of that species into the total system. So again, this let's say mu ice is partial G prime and ice. Okay, something like this. And you can say that if you add 1 mole of ice into this whole system, the G prime will be increased by a certain amount, right? And that can be expressed as a ratio like this. Okay, so this is the same as, this whole thing is the same as G ice. Or you can say this is delta G prime when adding 1 mole of ice. Right? Can be expressed as something like this. So as an increase of value of G prime, for one component system is simply the molar Gibbs free energy of I. So Gi is the same as mu i's, or you can say Gi is the same as mu I. Okay, we're just rephrasing the things that we already learned in chapter 5. And like I mentioned earlier, just only briefly, that when temperature is greater than 0 degrees Celsius, we know that the stable phase should be liquid phase, should be water. Therefore, the chemical potential of ice should be greater than that for water. Therefore, in that case, the Gibbs free energy, or you can say the molar Gibbs free energy for ice, should be greater than that for water or liquid phase, right? Something like this. Therefore, the escaping tendency of water or H2O molecules from the solid phase should be greater than that from the liquid phase. So in that case, so when you're dealing with T greater than 273 Kelvin, you should have, let's say, a greater arrow here, but only a small arrow coming back. Because more water molecules, or H2O, will be leaving the ice phase and go into water phase. Okay? So this is how you describe this kind of behavior using Gibbs free energy. So let us look at just the Gibbs free energy plot as a function of temperature. I think this is the plot for Gibbs free energy as a function of temperature will be a little bit different if you're using the newer version. For the older version, these two trend lines, which represents the Gibbs free energy for liquid phase water and solid phase water as a function of temperature, are more likely to be they're more like straight lines. But in fact, they should be having some sort of curvature. So if you look at the newer version of your textbook, these two lines should have some certain curvature. But unfortunately, if you're using the older version, you'll see something like this. But actually, in fact, the curvature is not that dramatic. So this is actually a more accurate, I believe is a more accurate plot. But to show you some concept, probably the schematic illustration in the newer textbook is more straightforward. But please bear in mind that these are not perfectly straight lines, and these should have some curvature. But if you look at a newer version of textbook, you should be fine. Okay. So this is probably the most important concept that we're going to talk about in this chapter, which is plotting Gibbs free energy as function of temperature. Or later we'll see that we're going to plot Gibbs free energy as a function of pressure. Okay, but in this scenario, as a title of this section, we know that we're dealing with constant pressure process. So right now, the Gibbs free energy is only the function of temperature. Okay, and now we're dealing with two different phases. We have liquid phase, which is water, and we have the solid phase, which is ice. And we already know that if when your temperature is higher than the melting temperature, which is 0 degrees Celsius or 273 Kelvin, the Gibbs free energy for the solid should be greater than that for the liquid. Right? So it is very straightforward that we know that if this is the melting point, or you can say for water it is 273 Kelvin. If it's greater than that, for instance, you can say like 50 degrees Celsius or at room temperature 300 Kelvin, let's say liquid. the Gibbs free energy for solid phase is greater than that for liquid phase. And we know that at melting temperature, these two things are the same, right? So then you can make a line, something like this. So this is the same as what we see in the slides. But in reality, if you look at a new textbook, it's more like this. It's having some sort of curvature. And more importantly, it is bending downward. So it means that using calculus, if you know the definition of curvature, it should be a negative. It should be a negative number. Okay, so this is the melting temperature, and you'll see these kind of curves. So the curvature is downward, and therefore it should be negative. So how do we know that it should be something like this rather than bending upwards? Why not like this? This is due to some thermodynamic properties that we can derive. So first of all, let us look at the slope. So recall that partial g partial t at constant pressure is simply minus s, right? So that's the reason why I said in this chapter, I think this is the most important thing. So at constant pressure, this is 0, and partial g partial t at constant pressure is simply minus s. So it is the entropy of that phase plus times the minus sign. So it should be a negative number, right? Because we know that entropy cannot be negative. So entropy itself, S of a substance, should always be positive. If you times that with a -1, then this number should always be negative. Which means that the slope of the curve that we plotted out should be always negative, right? Therefore, for liquid phase, for solid phase, these two lines, they are always having negative slope. They are not moving upwards. So that's the first derivative. Okay, the first derivative of Gibbs free energy as a function of temperature should always have negative slope. And moreover, if we take the second derivative, partial g partial t, and then take the derivative against temperature again, it will become Cp over T with a minus sign. And the reason for that is because if you take a derivative again, it's partial s partial T. It's partial s partial T. And we know that, I think I derived this before. So if you recall the first law of thermodynamics, TdS is du plus pdV. But in this case, if you're dealing with a constant pressure process, TdS is simply Cp dt, right? Or you can say this is dH. And therefore, partial s partial t, you simply move this term here, and this is constant. Just move over here, and this takes place at the constant pressure condition. Therefore, if you have a minus sign here, of course, you have a minus sign here. So this tells us that the curvature, which is the second derivative of Gibbs free energy against temperature, should be minus Cp over T. And we know that temperature should always be a positive number, and Cp should always be a positive number. Therefore, this is always negative. So the key points here are, first of all, if you plot G of T or Gibbs free energy as a function of temperature, for all substances, for all kinds of materials, the slope should be negative, and the curvature should also be negative. So that's the reason why we can be sure it should behave like this rather than something like this. They are always bending downward, and the slope is always negative. The slope is always negative. Okay. So in your textbook, I believe that if you're using the 6th edition, then the plot should be similar to this one, rather than straight lines. And we only discussed the temperature, above melting temperature previously. But if you look at the condition, below melting temperature, it's also very straightforward, because when the temperature is below 273 Kelvin or below the melting temperature, we know that the system of, at least in this case, if you're dealing with H2O, the system will tend to become just solid. So if you're over here, for instance, this is T less than T melting. We know that the system will become more and more icy. You have more and more ice. And in that case, indeed, the solid phase has a smaller Gibbs free energy while comparing to the liquid phase. Right? So here you have, let's say, G solid less than G liquid. But over here, this is T greater than T melting. You have G liquid smaller than or less than G solid. So this is a simple way to express Gibbs free energy of two different phases on the same plot and near the phase change temperature. And again, these two features are very important. The curvature and the slopes are both, should always be negative. So if you take the difference of these two lines, the values from here, and for instance, over here, the difference will be a positive number, but over here, the difference should be a negative number, depending on which kind of reaction that you're talking about. For instance, if you are dealing with solid to liquid phase, then you use the liquid phase Gibbs free energy, and then to subtract that with the solid phase Gibbs free energy. Therefore, in this scenario, this delta G here is G. This is G liquid minus G solid. Right? So in this case, we know that over here, liquid is less than solid, so G liquid minus G solid should be a negative number, but over here, it should be a positive number. And here, you have the difference being 0. Therefore, you'll see that here it is 0 at the melting temperature. And that is consistent with what we just stated in the very beginning of this lecture, that at the melting temperature, ice and water, these two components are in equilibrium, so the Gibbs free energy are the same, and therefore delta G of this reaction, if you want to call it, should be 0. And also recall that this is the slope should always be negative. That's also the same for delta G. And the reason why this is true is because this delta S is S liquid minus S solid, and times a minus sign. And we know that for liquid, they always have a greater entropy while comparing to solid. Right? I think that's also in the midterm exam that asking you to to directly calculate the entropy or the multiplicity of a liquid phase or solid phase, right? And so therefore, in this scenario, the liquid phase entropy is always greater than that for solid. So this is a positive number. But you have a minus sign in front of it, so this is always negative. So for this plot, this is delta G as a function of temperature. For this kind of phase change reaction or phase change behavior, the slope is always negative. The slope is always negative. And if we take the enthalpy into account, we want to see like what's going on at the melting temperature. We know that by definition, Gibbs free energy is enthalpy minus temperature times the entropy. And when we're dealing with just one component system, of course, we cannot change the temperature, saying that for liquid phase, like you have one temperature, and solid phase, you have one temperature. So they both share the same temperature. Okay, so in this case, for these two phases, the temperature will be the same, of course. If you confine them in the same space, they should have the same temperature. But the enthalpy and the entropy for these two phases might be different. They might be different. And for this kind of reaction, from solid phase to liquid phase transition, the delta G will be delta H minus T delta S. And temperature is the variable that we want to control, right, in this scenario. Therefore, at the melting temperature, we know that this delta G is 0, because we know that for two different phases, they should have the same Gibbs free energy, same chemical potential. So delta G is 0, and that implies, in this case, at equilibrium, at the melting point, delta H should be equal to Tm, which is the melting temperature, times delta S. So this is a very important expression or relation that allows us to simplify a lot of, calculations. And in fact, we've already seen this before, right? If you still remember, I think also in the last chapter, when we're talking about the boiling and the melting of solids, we want to calculate delta S. That's also in your midterm exam, right? So in this case, delta S is just the latent heat over the melting temperature. Right? This is the phase transition latent heat. This is the entropy change of that phase transition. And therefore, it is delta H over Tm if you want to calculate that. Okay. And if you know these quantities, typically these are given, then you can sort of try to derive delta H and delta S as a function of temperature. And this is what it will look like. We'll come back to this later. Let's just stop over here first. So previously, we tried to decompose Gibbs free energy, delta G, to become delta H minus T delta S. Okay, so the reason why I want to do that is because we want to see delta H as a function of temperature, and also delta S as a function of temperature. And we know that at the melting point, delta G is 0. Therefore, in that case, at that point, delta H is simply the melting temperature times delta S. And we used this relation before, try to estimate like how large the phase transformation entropy change is, right? As long as you have, if you can measure the latent heat of that phase transformation, and you divide that by using the melting temperature, then you can derive this delta S. That's what we saw in previous chapter. But here, like for instance, in the case of water, if you know some of these I would say information, for instance, the latent heat from solid to liquid phase, which is around 6,000 joule at this 0 degrees Celsius. And this is, of course, the melting, I'll say the latent heat for 1 mole of water molecule. And if you also know the absolute value of entropy for water in the liquid phase and solid phase, and also the heat capacities or the molar heat capacities for water in the liquid phase and solid phase, which are constants in this case. And if you know these information, then you will be able to estimate what will be delta H and delta S at different temperatures, right? That's what we try to do in chapter 6. So as long as you have delta H at some certain temperature, then you should be able to estimate delta H as a function of T, as long as you have the information of, let's say, delta Cp, right? And recall that let's say if it's, in this scenario, it's 273, then you can express delta H as a function of temperature at any different kinds of temperature as the add-on, of the original delta H you have. So this is, I believe, in a lot of your midterm exams. And but in this case, we already know the difference between Cp should be independent of temperature. At least this is what the example tells us. Then this will only be a constant and then times a temperature difference. So this will be a linear change if you plot it out, if you're using these numbers. And for entropy, you use the same thing, right? For entropy, let me write it down over here. For delta S, it is also at some certain temperatures, delta S, let's say 273, plus like delta Cp over T. Oh, sorry, it's 273 to some certain number. So it really depends on like what kind of temperature, initial temperature that you have. Maybe for this case, we need to use 298, right? For instance. So these are what we learned in chapter 6. So if you use that knowledge, and then if you try to calculate delta H and delta S as a function of temperature, so these are just the details. But the key point here is try to derive delta H and delta S as a function of temperature, and then plot it out. So this is what you will see if you try to calculate these things as a function of temperature. We know that the difference of Gibbs free energy is, again, delta H minus T delta S. And both these are function of temperature, right? This is delta H of T, and this is delta S as a function of temperature. And based on the information given, we can calculate that. And if we plot delta H as a function of temperature on the same plot of delta G as a function of temperature, we'll see that delta H has this kind of upgoing trend. And more importantly, when you go down to 0 Kelvin, you'll see that these two curves will converge to the same point. And this is what we learned, I think, back in chapter 6, when we talk about the third law of thermodynamics. We've seen the exact same plot before. But at that time, I'll only have delta H and delta G plotted out. In this case, we also have the T times delta S.
T times delta S. And we know that if you look at delta G, it should be something like this. This is what we already saw earlier today. And we know that if it's above, if the temperature is above the melting temperature, then delta G is less than 0. It should be a negative number. And therefore, T delta S should be greater than delta H, right? So T delta S should be greater than delta H when the temperature is above the melting temperature, right? So this curve should go up and go beyond delta H. I believe that this probably is not shown up in your new textbook. So if you want to just add it up, I think it's fine. And of course, at the melting point, we've already derived that, right? Because delta G is 0 at this point. Therefore, delta H at the melting point should be the same as Tm times delta S. Something like this. So at this point, these two curves should converge to the same point to make delta G 0. If you go below the melting temperature, of course, these two lines will separate again, but only delta H is greater than T delta S. So in that case, delta G will become a positive number, And eventually, when you go down to 0 temperature, because delta H is essentially the same as delta G, so there's no contribution from delta S at all. Remember that when we argued this in chapter 6, we say that at 0 temperature, all the entropy should be 0, right? For all substances, ideally, they should go down to 0 entropy. Therefore, delta S should also be 0, right? Ideally. Of course, in reality, we know that there must be some finite entropy at 0 Kelvin because there's an imperfection of material or substances at 0 Kelvin. But ideally, delta S should be 0. So again, T delta S, this is, let me, this should go down to this. The T delta S should go to 0. And therefore, delta H and delta G will converge to the same point. Sorry, this is not 0. The 0 is over here. So T delta S has this kind of behavior. So this is more straightforward. So if you are using the previous edition of the book, you have this kind of plot. But it's not extended to 0 point, which I think is not complete. But if you're using the new version of the textbook, it doesn't show the contribution from T delta S. So I think it's good that if you can have the full picture. And this is also consistent with what you learned in the previous chapter. Okay. And we know that when the temperature is above the melting temperature, the dominating term is delta S. So the entropy term, typically they will say qualitatively that the entropy term is dominating. When it is below the melting temperature, the delta H term, the enthalpy term is dominating. But it's really not that necessary. We can just say it's the competition of these two things. And when these two terms are having the same value, then we know that's the equilibrium point where delta G is becoming 0. Okay, so you can go through these by yourself, but eventually, if you schematically plot it out, it should have this kind of trend. But if you look at the calculation, it seems to be tedious, but it's actually not as complicated as what you went through in the midterm exam. Okay, so the equilibrium requires that G prime. So if you're using the total Gibbs free energy again as your measure, of course you're using the G prime, not instead of the delta G. So if you're using G prime, then it means that the G prime of a system have its minimum value at a given T and P. So at this part of the textbook, it seems to be complicating and confusing because sometimes it is using G prime as your measure, sometimes it's using the delta G. So what's the difference between these two? So if you're using G prime, this is the total Gibbs free energy. If you're using delta G, this is the, you can say this is the reaction Gibbs. This is what I call them typically. So if, depending on which route you are going through, you will have different kinds of criterion to define equilibrium. So if you're using G prime as your total Gibbs free energy, this means that this is like, for instance, N1 plus G1 plus N2 G2. And in this case, this is G2 minus G1. Right, so these are two different things. Here and here. So what we've been discussing, for instance, in this plot, we have delta G as a function of temperature. Actually, we're talking about this thing. So the equilibrium point, for instance, at the melting temperature, Tm, G2 will be the same as G1. And at that point, delta G will be 0. But at a constant temperature and constant pressure, it means that the temperature, if the temperature is fixed and the pressure is also fixed, then what we try to minimize is actually this thing. We're not talking about reaction, we're talking about the minimization of Gibbs energy for different species. Okay, so we're talking about different things. So when talking about equilibrium, for instance, over here, we use delta G and we say, okay, so delta G should be 0, over here. But if you're using G prime as your measure, we're actually trying to minimize this thing. So at a constant temperature and a constant pressure, this thing should be minimized. This thing should be minimized. And what does that mean? If you're looking at here, this delta G is taking the both species into account and measure the difference of their Gibbs free energy. But if you are using this criterion, you are using the sum of the Gibbs free energy. So that's two different ways of thinking when trying to figure out the equilibrium point. Unfortunately, the textbook doesn't go into too deep about like what G prime is, because it's not the focus of this chapter, right? Because like I mentioned earlier, this is one component. For this chapter, we're dealing with one component system. So of course, you can say this is the G1 is for water, and this is for ice, like I mentioned earlier. But this is not a very useful way to describe equilibrium point. Instead, in this scenario, delta G is a better measure. Delta G is a better measure. So in words, we say equilibrium requires that G prime for the system have its minimum value at given T and P. But we didn't actually go through, we didn't solve like what will be the equilibrium values for instance, N1 and N2, right? We didn't solve for that. We're actually only dealing with this thing. So in this chapter, we won't use this criterion to do any calculations. Okay, and minimization of G prime requires that G be small and S be large. That's also what we learned when we first introduced Gibbs free energy, right? When we talk about the chemical equilibrium, we say the enthalpy should be small and also the entropy should be large to minimize G prime, to minimize this thing. Okay. So the reason why I stress I focus on these things to make a point about these things because sometimes in this textbook, it will confuse you by using either G prime or delta G to talk about equilibrium. But just to make sure that when we plot this kind of Gibbs free energy as a function of temperature, it means that we're using this as our criterion of equilibrium. We're not using the total Gibbs free energy of the system as our criterion for judging equilibrium. Okay. So equilibrium between two phases occurs as a result of comprise between enthalpy consideration and entropy consideration. So if we go back to this plot, we'll see that, again, there's a competition between enthalpy term and entropy term. At some certain point, delta G will be 0, such that these two things can coexist. But it does not mean that this is the only equilibrium point, because by changing the temperature, you'll see that equilibrium will change. From here to here, it really depends on the temperature of your system. So we've already discussed the Gibbs free energy as a function of temperature, and now we switch gear to talk about Gibbs free energy as a function of pressure. So again, at the very beginning, I state that the Gibbs free energy is a function of two independent variables. So if you're just dealing with one component system, for instance, just water, temperature and pressure will be the two independent variables. And we've already discussed, for instance, over here, the Gibbs energy as a function of temperature. And now we want to talk about Gibbs free energy as a function of pressure. And we call that partial G, partial P is just the volume, or you can say the molar volume of the material. Therefore, if you're, again, dealing with this kind of phase transition, so from the solid phase to liquid phase, you have partial G liquid, partial P. That will be the molar volume of your liquid phase. And partial G, partial P for the solid phase will just be the molar volume for the solid phase. Okay, so partial delta G, partial P will be the molar volume change from liquid to solid phase. So for instance, if we are dealing with a transition from solid to liquid, which is the melting process, so the delta V will be related to VL minus Vs, right? The final state molar volume minus the initial state, which is a solid state, solid phase molar volume. And this is where the interesting thing will happen, because we know that for water, if you're in the solid phase, if you're dealing with ice, the volume is actually bigger. The molar volume is actually bigger than water, right? Because we know that when you freeze a bunch of water, the volume will be expanded. This is different from other kinds of materials. So for instance, later we'll see that if you're dealing with carbon dioxide, we know that when you cool it down and then to form the dry ice, the volume actually will become smaller. So most of the normal materials, typically when you freeze your material down to solid phase, typically the molar volume will become smaller, right? But water is an anomaly. It's a very different case. So the liquid phase will actually have a smaller volume while comparing to the solid phase. So ice will have a larger, because it has a less density. So the ice will have a larger molar volume. So in fact, this number will be negative. But for most of the materials, other materials, this actually will be a positive number. Later we'll see that. So the rate of increase of Gibbs free energy with an increase in pressure at constant temperature equals to the molar volume of the phase at a given temperature and pressure. And the ice melts when the pressure is increased to a value greater than 1 atm. So for water, or for water molecules, this is a very interesting case. When you increase the pressure, actually the water will tend to form ice. When you increase the pressure, the ice will tend to melt and become water. So this is different from other materials. So let's say this is at temperature is fixed at 0 degrees Celsius. And if you increase the pressure, ice is actually having this tendency to become water, and that trend will be greater than, that tendency will be greater than water becoming ice. Which means that if you keep increasing pressure onto ice, they will be melted into water. This is very counterintuitive because when you increase the pressure, typically you think that you are forcing the atoms to become closer to each other, and therefore they should be more preferable to become solid. But that's not the case for water molecules. Okay, and if you plot the Gibbs free energy for liquid phase and solid phase water as function of pressure, this will be what you have. So now the axis will be pressure. Again, we have two phases, and here it is 1 atmospheric pressure. We know that by increasing the pressure, ice tends to be melted into water. So the liquid phase should have a smaller Gibbs free energy. But in most cases, the trend line of these two curves should be flipped. So for most, so this is for water, but for other normal materials, this is the liquid line, this is solid line. This is for other regular materials. And this is for water, for H2O. And we've already seen that this is, the slope is partial G, partial P at a fixed temperature is related to the molar volume, right, V. We've already seen that, okay, over here from the derivation earlier. And this is always a positive number, right? Volume cannot be negative. So since the molar volume is always a positive number, therefore you can see that the slopes over here that we plotted out should always be going upward because the slope is positive. Okay. And again, textbooks stress that note that water is an anomaly, that typically the melting causes an increase in volume, but that's not the case for water. We know that the ice has a greater volume. So if you melt ice, the molar volume actually will become smaller. Therefore, for water, you'll see that this line later will we'll explain and we'll derive the trend line for this one. You see that because when you're here, this is the let's say this is 760 millimeter. This is what is this? Mercury. This is the 1 atmospheric pressure over here, and this is 0 degrees Celsius, and this is 100 degrees Celsius. So this is the regular freezing point, the regular boiling point. And if you start from here, and then if you increase the pressure, which means that if you go upward from here to here, you will become just a purely liquid phase. Right? If you increase the pressure, let's say originally you are here, and if you increase the pressure, you'll go across that borderline of the two phases, and you'll enter the pure liquid phase, which means that when you increase the pressure, typically you will get more water than ice. And for regular materials, typically you'll have a positive slope. Okay? Here you have a negative slope because this pressure as a function of temperature is that this borderline is actually going up to the left, so the slope is negative. But if you're looking at, for instance, carbon dioxide, like I just mentioned, the slope of this borderline is positive. So it is going upward from the triple point to not the infinity, but to very high pressure. So if you increase, let's say you start from here, and then you increase the pressure with a constant temperature, you will go across this border and you'll evolve from liquid to solid. So if you enforce a huge pressure onto carbon dioxide liquid, if you can have that kind of form, they will become solid. They will become solid. But of course, at regular pressure and temperature, we're over here, right? If you remember from your common sense, that for carbon dioxide it's so-called dry ice. So if you have carbon dioxide as a solid form, if you take that out to at a room temperature at regular atmospheric pressure, they would just it will just go through this sublimation process. It will just become gas directly. So in the regular condition, we're at this point. We're at this point. But in the case that if you have a very high pressure and if you have the liquid form, like when you further increase the pressure, you will get more and more solid phase. And you can see that this line is having a positive slope going upward. So we can derive and to predict this border or this boundary line by using, like for instance, the pressure as a function of temperature. And that's what we're going to derive next. So Gibbs free energy, eventually we want to see that as a function of both temperature and pressure. So very intuitively thinking that we just start from the equations that we have because dg is minus dt plus vdp. This is what you learned in chapter 5. And more importantly, at the equilibrium point, not only the Gibbs free energy for liquid phase will be the same as solid phase. So if you're dealing with, for instance, this point, we know that G solid is the same as G liquid. And more importantly, dg is the same as dgl liquid phase is the same as that for a solid phase, dgs. Of course, if you look over here, you'll say that it seems not to be the case, right? Because if you move Gibbs free energy a little bit away from this point, the Gibbs free energy over here is not the same as the Gibbs free energy over here. But that's not we're not talking about this case. We're talking about moving along this borderline. Okay? So don't be confused by what it says. So for instance, if you're dealing with a phase diagram like this, let's say just like water, maybe something like this. This is solid and liquid, and this is gas. And let's say this is for instance, something like, sorry, this is pressure. Okay. The equilibriums, this equilibrium means that we're on this line. So when you change your pressure, if you want to stay on this line, you have to also change your temperature. So the goal here, typically if you state the goal first, it's much easier for you to understand what we're going through here. So eventually we want to find pressure as a function of temperature along this, let's say, let's say just equilibrium line, or the order of two phases. So essentially, we want to see this order, which is, for instance, in this case, you can say this is a pressure line, as a function of temperature, right? Of course, you can, reverse this by 90 degrees and then say this is temperature as a function of pressure. But it's more intuitive, or it's, conventionally, we want to say this is pressure as a function of temperature. So along this line, actually, the Gibbs free energy should always be the same for liquid phase and solid phase, right? Because along this line, we know that the two phases can coexist. And more importantly, a small change along this, when you move along this line, the Gibbs free energy for the two phases are actually changing. But the changing rate, when you move from this point, for instance, to this point, are the same. Therefore, dG for liquid and for solid will be the same, right? So, for instance, if you start from here, this is point A, and we start over here at point B. So at point A, you have G solid at one temperature and one pressure, and that should be the same as G liquid at this temperature. Let's call this TA, PA. And that will be the same for point B. But that does not necessarily mean that these two should be the same, right? And we know that it should be different because we already changed the temperature and pressure to a different value. So the Gibbs free energy of that solid phase should be different, from the, at the original point. But it should still be the same as the liquid one. So the change, from here to here, and from here to here, is dG solid, dG liquid, should be the same to make sure that this equal sign is still valid. Right, so please bear in mind that here when we talk about dg liquid is the same as dg solid is because we're moving, we're talking about a condition along this borderline between two phases. Okay. Otherwise, if you're dealing with other types of condition, if you're moving from here to here, of course we know that dg won't be the same for solid and liquid phase. Only when you're moving along these border lines, you can state that the dg's will be the same. And therefore, we know that dg is minus s dt plus v dp, and therefore we'll go through these derivations that you will see on textbook. So for the equilibrium to maintain, we also have this condition. These two should be the same, so we can write these down. Okay, for the liquid phase, it's minus S liquid times the change of temperature plus the molar volume of the liquid phase times dP, and that will be the same for a solid phase. And we know that this dP, dPs are the same for these two sides of equations because we're moving on the same plot and moving from here to here. So we're dealing with the same change of temperature and pressure. And eventually we'll arrive at this very important relation, because if you move the terms around, then you realize that you can figure out the slope of pressure against temperature. And that's what we want, right? Eventually we want to find pressure as a function of temperature. So we can start from dP over dt, let's say at the equilibrium. Along this equilibrium line, or you can say along this border of two faces. And through the knowledge from chapter 5, we derive that dP dt is actually related to the change of entropy over the change of molar volume. Okay, and this is, for instance, from solid to liquid phase, and this is from solid to liquid. It really depends on which side you want to start from. So over here it's liquid to solid, but I typically prefer solid to liquid because it's a melting process, and you go to positive temperature. And this equation can be further simplified to delta H over T over delta V. And the reason why we can do that is because we know that at equilibrium points or along this line, the delta G is always 0. Therefore, delta H is T delta S. And here we have delta S, so it's delta H over T. So eventually you'll have an expression for dP over dt that can be estimated by these macroscopic measurables. So these quantities, for instance, delta H, will be the latent heat of phase transformation, right? And this quantity can be measured experimentally. And that's the same for this molar volume change. As long as you can monitor the change of volume, then you can estimate this using experiment. So eventually you can predict this kind of line, the trend of this line, by measuring the delta H and delta V under different temperature and pressures. So this is very important. So whenever you carry out an experiment, for instance, under different temperatures, and then you measure the latent heat change and also the molar volume change and record that, and if you have enough data, you should be able to map out the trend line for this because you can derive dP over dt using these quantities. This is called Clapeyron equation. And later we'll see that the other types of Clapeyron equations for instance, this line and this line. But right now we're just dealing with solid to liquid phase transformation. And this is what we call Clapeyron equation. And this is probably the most important thing in chapter 7 because a lot of calculations will be based on this. So for instance, the problem will give you, for instance, a molar volume for solid phase and liquid phase, and also the latent heat of this phase transformation, and then ask you to calculate dP over dt. Okay. And more importantly, if you know delta H, delta H as a function of temperature, and also delta V as a function of the temperature, then you can integrate the right-hand side over temperature and then directly derive pressure as a function of temperature, right? So the Clapeyron equation states that dP over dt, so at equilibrium, is, let's say, delta S over delta V. I would say solid to liquid. So when you calculate this, you use the liquid phase entropy minus the solid phase entropy, unlike what we have over there. If you write this like this. So this is solid phase, the liquid phase minus the solid. And this is, and this is further converted to and let's say this is from solid to liquid. So let us consider the case of water again. Actually, we've been always talking about water since today. For water, we know that delta H from solid to liquid is what? Positive, right? For water, of course, delta H from solid to liquid is greater than 0, right? Because you need to absorb heat in order to melt ice into water. So we know that delta H should be greater than 0 for water. But delta V is what? Again, when we talk about this is the molar volume of liquid minus the molar volume of solid. And if you still remember what we stated earlier, that water is an anomaly, right? So liquid minus solid is a negative number. Okay, so this is a negative number for water. If you're dealing with carbon dioxide, then this will be a positive number, right? But now we're dealing with water, so this is a different case. So eventually, this term will be negative for water. So here, along this line, the slope will be negative. dP dt, which is the slope of this borderline, should be negative because we have this molar volume change from solid to liquid phase being negative. But if you're dealing with, for instance, carbon dioxide, which is a regular material, and when you melt it, typically when you melt something, into liquid form, the volume will become bigger. Therefore, this is a positive number. Then you'll get a positive slope. Because dp dt, by that definition, will have a positive denominator. Therefore, this number will be positive. Okay, so that's the reason why if you're dealing with water, you'll see this negative slope over here. But if you're dealing with like carbon dioxide or other types of metals, you'll see this kind of a positive slope. So that's the difference between regular material and water. And that can be seen or predict by using this Clapeyron equation. And more importantly, like I just mentioned, if you know the temperature dependence of this and also this, you'll be able to explicitly derive pressure as a function of temperature. What does that mean? Let's say this. Let's erase this. We know that the ultimate goal is to figure out this pressure as a function of temperature, right? So if you know this is a function of temperature, T. This is also a function of temperature. Of course, you can do this. And then, if you do the integration for both sides, then you know like what you're dealing with for T from T1 to T2, for example. And then you will have the expression of pressure as a function of temperature. So this is a general thought of what we're going to approach in order to get pressure as a function of temperature. But typically, like if you have dP over dt, then you can already predict what the trend should be. It should be a negative slope or a positive slope. So this is known as Clapeyron equation, and it actually tells you the trend line, what the trend line should go between these two different phases. And for water, like I mentioned earlier, since delta S to liquid is negative over here, therefore the slope is negative. So an increase in pressure decreases the equilibrium melting temperature. Okay, so increase in pressure will decrease the melting temperature. The slope is negative. So that's the reason why people say, like, why ice skating is possible. The pressure, if you have an ice skating experience, you know that you have this blade that you wear on your feet. And when you step on ice, you're actually enforcing a huge pressure onto ice. And that will cause the ice to be melted because the pressure has been increased. And if the pressure has been increased, it's more likely that the ice will become water. Therefore, it's more slippery and allows you to skate over ice. But is that true? I don't know. I mean, this is what people, at least in the textbook, states that this is because of that. I think probably this is a myth because when people talk about like how the plane can fly, they will talk about like the Bernoulli principle. But actually, that is not really explaining why the airplane can fly. So the reason why airplane can fly is probably not related to any high school physics. This is true. You can look it up. So I'm not sure if this is true. Like this is really related to thermodynamics. But this is probably the only real life example that you will see in this textbook, in this whole semester. So you can look it up. I don't trust that at all. I don't think this is true, but I don't know. For most materials, of course, it will be the opposite. If you have more pressure, it will become more solid. So it will act in the opposite way. Okay. And of course, eventually we want to see Gibbs free energy as a function of both temperature and pressure. And we'll see that later in 10 minutes. So eventually we want to see Gibbs free energy as a function of both temperature and pressure. And therefore, you have to plot it out as a three-dimensional way instead of using like two-dimensional plot. For instance, Gibbs free energy is a function of both temperature and pressure. So you have two axes, temperature and pressure, and then the third axis as the Gibbs free energy. So if you look on textbook, you see this kind of plot that you have temperature and pressure, and the Gibbs free energy is kind of surface. Okay, it's a two-dimensional surface, and in this case, you'll see that this solid line represents the boundary of the solid phase. Okay, this is the Gibbs free energy of the solid phase. And then you have this liquid phase, which is a different plane. So each plane represents the Gibbs free energy of each phase. And when these two phases, when they have an intersection, it will be a straight line. And that straight line corresponds to this line. This is what we saw on the phase diagram, right? So not sure if it's possible to express this here, but for instance, if we consider it here, this plot again, I will say this is, let's see, it's hard to see, but let me think about how to express this. Let's say this is liquid, the plane of liquid, and here is the boundary line. And here, this is another plane for the solid. Is this clear? Maybe here. Not sure if this is clear enough, but maybe not. But I think it's so hard to plot it out in a three-dimensional way. Maybe I should practice first. Maybe this is more straightforward. Yeah, like this. So you have two planes, right? You have two planes, and they intersect with each other, and then they will form a line that is the line for the same Gibbs free energy, right? So, for instance, if this one is the Gibbs free energy for a solid, and this is the Gibbs free energy for liquid, this plane, and this one. So we know that, for instance, over here on the right-hand side, the liquid phase has a smaller Gibbs free energy when compared to the solid. But if you're over here on the left-hand side, the solid one will have a smaller Gibbs free energy. But it really depends on how you, like which axis you're looking at. So here, if you're looking at these two planes from this side, with a fixed pressure, if the pressure is fixed, then you're just looking at this plane over here. Then at constant pressure, then you will see this kind of cut, I would say the cut face. And these two lines, let's see. So these two lines, the liquid and solid lines, are, you can say the cross-section, of these two surfaces. You map that onto just one pressure. Okay, so there will become just two lines as a function of temperature. So imagine that, let's say you have a cut face for this one, then you just see two lines, right? You just see two lines. So this is the line for instance, for liquid, and this is the line for solid. Okay. And if you cut this, from a different direction, for instance, at a fixed temperature, and the only variable is pressure, then you'll see it a different way. Okay. So basically, if you want to include both variables like temperature and pressure, then you have to think of Gibbs energy as a two-dimensional surface in a three-dimensional space. But if this is too complicated for you, of course, you can go back to, you can cut down one dimension and then just go back to the original argument that consider one variable fixed, and then just by changing the other variable, for instance, fix the pressure and then change the temperature, then Gibbs free energy will just be the function of temperature, which is maybe much easier for you to understand. But of course, if you have this kind of picture in mind, then you can view from the top, right? If you view from the top, then you'll see that this is actually the line that corresponds to, for instance, this border. Okay, this border over here. Okay. And what we just mentioned is the phase transition between solid to liquid phase or liquid to solid phase. And now we're trying to look into the solid to vapor or the liquid to vapor phase transformation, which means that there's a huge change in terms of volume. Because we know that if you're transforming from liquid phase or solid phase into vapor phase or gas, typically the molecule will try to escape, and there's a huge change in terms of the molar volume. So in that case, if you're still using the same derivation process, you'll see that delta V is actually close to the volume of vapor. Because when you're dealing with the phase transformation from condensed phase into the vapor phase volume is always much greater than that for the condensed phase, either liquid or solid. So previously, we're dealing with the phase transformation from solid to liquid, right here from here. Now, if you're dealing with the phase transformation from either solid to gas or liquid to gas, then delta V will be much greater than the V of, say, liquid over here. And this delta V will also be much greater than V solid. Therefore, you can say these delta V is close to just the molar volume of gas. Or in textbook, it says it's a vapor, okay, vapor phase. So the Clapeyron equation again can be written as delta H over T times delta V, but in this case, because delta V is approximated as V vapor, so it will become something like that. So the Clapeyron equation will be originally is delta H over T times delta V, but in this case, if you're dealing with condensed phase to vapor phase transformation, then this is approximately the volume of the, let's say, gas or vapor. And of course, if you're dealing with, say, like an ideal gas, this can be further simplified, right? Because if you're dealing with ideal gas, then you have the ideal gas law that PV equals to RT if you're dealing with just a mole of gas molecules. So that will further simplify this because we know that P times V is RT for gas. Therefore, volume is simply RT over P. Therefore, this is, and this is R times T over P. Something like this. And you have two T's, so this RT squared. So this is much simpler. So as long as, again, you know delta H is a function of temperature, then you can do the integration. But in this case, of course, you have to remember that you have to move this pressure to the other side to do the integration. And that's what we're going to go through. If you move the terms around, okay, then eventually you arrive at this equation. Like d log P is delta H over RT squared times dt. So this is directly, that result is directly derived from what we have over here. If you don't know, this is, I'll ignore the some terms over here. Therefore, if you move this to over here, okay, so this is, eventually you have something like this. Or if you want to use d log P, it's the same thing, right? Because dP over P is d log P. And this is what we call the Clausius-Clapeyron equation. And this is only valid when you're dealing with condensed phase to vapor phase transformation. So if you're dealing with the line over here, like we mentioned earlier, like if you want to figure out the trend line over here, you cannot use this equation because this is only valid for the condensed to vapor phase transformation because we use this approximation over here, right? And we know that for solid to liquid phase transformation, there's no such huge change in terms of molar volume. So you cannot use this. You cannot use this expression, or this. You cannot use this approximation. Therefore, you cannot use this expression. So if delta H is independent of temperature, in most cases, delta H will be dependent on temperature. But if it is independent of temperature, and if the molar heat capacity of the condensed phase is the same as the vapor phase, which means that delta Cp is 0, then this is just a constant and it's independent of temperature. So therefore, if you do the integration, it is only the integration over this T square inverse. So eventually you'll have a very simple form, which is log P being minus delta H over RT plus an integration constant. So this is a probably not so useful expression because typically delta H is not independent of temperature, and typically the molar heat capacity for condensed phase is not the same as the Cp for vapor. So, but this is just a an expression that gives you a hint of what the pressure over T, what the pressure dependence on temperature should look like when you have this vapor phase approximation. For instance, eventually you have log P being, let's start from there. So d log P as delta H RT squared plus dt. So if delta H is a constant, which means that we don't have to worry about any temperature dependence. And also, if delta Cp, this implies that delta Cp is also a constant. We don't have to worry about this. Then log P will be just delta H RT minus. And you have a constant, right? You have a constant. So, which means that the pressure as a function of temperature is, I want to write it here. It's an exponential minus delta H over RT times some certain constant. Right, because if you have exponential term over here, exponential and it's a constant over here, then it's exponential times some other types of constant over here. So you know that it's exponential decay. Exponential decay is a function of delta H. But since the temperature is in the denominator, therefore, when you increase the temperature, actually this is the pressure will increase, right? So this one, this tells us that when temperature is increasing, then the pressure will also increase. If you plot this out, you'll realize that when you increase the temperature, because this will become a smaller and smaller number, and this has a negative sign, so pressure is actually going bigger and bigger. Okay? So when temperature is increasing, the pressure is increasing. And that is at least consistent with what we expect, that we should have this kind of positive trend. And so the value of pressure at any temperature will be the saturated vapor pressure exerted by the condensed phase at temperature. So this is essentially the definition of saturated vapor pressure, right? At some certain fixed condition, there is a certain pressure that exists in the vapor phase, and under that certain vapor phase, with that pressure, these two phases are in equilibrium with each other. So that's the definition of saturated vapor pressure. And we know that it increases exponentially with increasing temperature, like what we just mentioned over here. Okay, although it's in the inverse sign over here, but this is a negative sign, so you would think that it's decreasing, but because it's in the denominator, therefore, it's actually an increasing trend. So when you increase the temperature, the vapor pressure will increase dramatically. But in reality, typically, there's a difference between heat capacitance or molar heat capacity for the condensed phase and the vapor phase. So in this case, if there are Cp for the evaporation or sublimation, so evaporation means here, and sublimation is from solid to vapor, right? If for these two processes, or for one of the processes, delta Cp is not zero, but let's simplify it a little bit more, that is independent of temperature, then we know that we can use this expression. And if you use this expression, delta H as a function of temperature, this one as a function of temperature, we know that this is the standard condition plus delta Cp times the temperature difference. Right? This is what you've done a lot for chapter 6. And eventually you will have a constant term plus something that is linear proportional to temperature. Okay, so here this is a constant, and here you have a term that is proportional to the temperature, but linearly. So log P eventually will have something, related to 1 over T, and there's also a term that is related to log T, or nature log T. And of course, again, you have an integration constant. But, this is not very important. What important is, typically you can simplify that into a general form. Therefore, the vapor pressure or the saturated vapor pressure, if you take a log, typically is a function of temperature. And it can be expressed like this. You have some sort of log term, and you also have this term that is proportional to the inverse of temperature, and of course you have some constant. So if you want to approximate or empirically fit your experimental data, then this is a very good start. You typically start from this kind of expression. So this is similar to what we've learned earlier when we talk about the for instance, we start from the analytical form of molar heat capacity. We want to figure out what Cp of T is, right? And then, but we went through some derivations, but eventually we would say there's an empirical form, empirical expression that Cp of T is like A times, for instance, T to the 3 plus B T to the minus 5 or something like that. This is an empirical form that you can fit to your experimental data. And here is the same, like we want to know what's the exact expression for saturated vapor pressure as a function of temperature, but typically you just measure the data and you fit your data with an empirical form. And this is the form that people typically would use. So for each line over here, for this line and for this line, you can have different kinds of A and B and C. Okay. And typically if the problem asks you to calculate or to estimate something, then typically they will give you enough information which allows you to figure out what these constants are. Okay. So a graphical representation, I'll skip this a little bit and just go to, no, I don't think I have it here. Next time I will show the thing I plotted by myself. To go through this it's pretty straightforward. It's just go through the same thing again that we derived earlier, that for Gibbs energy, we want to figure out what delta H at different temperature is, and also like for instance delta S. But over here, the only information that we need is delta H as a function of temperature, right? Because here, this is the expression that the derivation that we end up with. And as long as we can have delta H as a function of temperature, then we can calculate the explicit form of pressure as a function of temperature. And that's what these derivations about. If you know the Cp of water, then you can, water and water vapor, then you can estimate the delta Cp as, this is a delta Cp as a function of temperature. Then you can estimate or calculate delta H as a function of temperature. This is what you went through for the chapter 6, right? And eventually you have delta H evaporation of water as a function of temperature like this. Again, you have a constant term. You have one term that is linearly dependent on temperature and to the squareness of, to the square of temperature, and also 1 over temperature. So this is very, very typical. But of course, the most important thing is that you want to calculate this. So you plug that into this equation, and then this is what you will get after you carry out the integration. Okay? So you'll see that there's a term that is related to, for instance, the inverse of temperature, for instance, over here. And this is related to log T, and this is linear to temperature, and this is to T to the minus 2. And then you also have a constant. So you see that you have at least 4 different terms, and you also have a constant. So you have 5 terms over here. So it seems to be a complicated expression. If you directly derive the expression from delta H as a function of temperature. But there's one thing that we need to determine first, which is this constant C, right? We don't know what this C is. I mean, all the other things is already settled, right? Because although you have R over here, but we know that this is just gas constant, and it is 8.314, so you can just plug in and then directly calculate that. But one thing that we don't know is this constant that is caused by the integration. So in order to do that, we have to feed plug in some experimental data first, which allows us to determine this constant. And that thing is the boiling point. So later you'll see that for some questions or some examples, typically they will give you some information which allows you to determine that constant first. Okay, so that constant is important. Or understand how to calculate that constant is important. And in this case, which is the standard problem, we know that the boiling point is at 1 atmospheric pressure, and it is at 100 degrees Celsius, so which is this point. So at this point, we know that this is 1 atmospheric pressure, and this is 100 degrees Celsius, which corresponds to 373 Kelvin. So then you know what you should plug in to calculate the constant C, right? Because over here, temperature, you will plug in 373 Kelvin. And on the left-hand side for the pressure, the log P, you know that you should plug in 1. You should put in 1 atmospheric pressure over there, and then you can calculate C. So eventually, I think the textbook shows you that this is around 50. This is around 50. So eventually, you will have an expression of the pressure as a function of the temperature. So all you need to do is plug in temperature, then you can know what the saturated vapor pressure is. And more importantly, typically people want to express this pressure as log P with the with a base of 10 rather than the natural log. So you have to know how to transform this to log P. So this is using 10, right? I think this is probably divided by 2.3 or something if you want to calculate. This is a simple math. It shouldn't be too hard for you. But eventually, in typical experimental data, if you want to fit it, people typically use the log P with a base of 10. But personally, to do calculation, I'll prefer nature log. I don't know which one is more intuitive to you, but I prefer this kind of nature log to do calculation because it's much easier to type in your calculator. So that's my personal preference. But just bear in mind that typically the problem, sometimes they will give you this kind of form, which is using 10 as a base for the log, but sometimes it's using the nature log. So please bear in mind that read the line carefully and figure out which one the problem is using. So typically for experimental data, if you want to do curve fitting, you will use this simple form. So you won't use that complicated form that you saw earlier in the slide. So you have too many terms, right? You have one term that's proportional to inverse t squared, and it's linear to t. There's a log t, and there's also t inverse, which is having too many terms. So most of the time, we only want to have like maybe 2 or 3 terms at most. So eventually, people pick this kind of expression. You have inverse of temperature dependence, you have a log t dependence, and that's it. That's all. And then, of course, you have a constant term. So if you use that to fit the experimental data for water, and this will be what you get. So if you compare this to what you have earlier, just using all these complicated terms, you'll see that this number is close to this one. And the log term, minus 2.37, will be turned into minus 4 point something. The order of magnitude is correct. And the constant term is 19.7 over here, but if you derive that explicitly, you get like around 22. So it's not that far off. Okay, it's not that far off. And it still gives you a very good fit. For instance, if you plot it out, if you're using this original term, the original expression, which has like 5 terms, you'll have a line that is very much the same as using just 3 terms. Only when the temperature is low, so here is the inverse of temperature. So here means that the temperature is low. When the temperature is low, there's a huge deviation. But when the temperature is high, the approximation seems to be pretty good. Okay. So eventually, people typically just use this kind of expression to fit their saturated vapor pressure. Okay. And so the agreement between these 2 expressions is good for high temperature, but the deviation starts to increase when you go down to lower temperatures. And one component phase diagram with T and P as coordinates is this kind of thing. And we've already mentioned the solid-liquid phase borderline, and now we also finish this line over here using the approximation that we used earlier. And the equation that we use is the Clausius-Clapeyron equation. So these 2 things are different. The Clausius-Clapeyron equation includes the approximation that the molar volume of vapor is much greater than the condensed phase. And this was not employed in the previous Clapeyron equation. So please bear in mind that there's a huge difference between these 2. Okay, so if we look at, so let us go back to this phase diagram again. There are some terms that we want to just define. For instance, the triple point, I believe that most of you, I think all of you already know that, which is the point that you have 3 phases that can coexist with each other. You can have ice, liquid, and ice, water, and water vapor coexist at the same time. But of course, that's not in the normal condition. Normal condition means that you're at 1 atmospheric pressure, and it's either at 0 degrees Celsius or 100 degrees Celsius that you can have coexistence of phases. But even with that, you can only have like 2 phases coexist at the same time. If you want to have 3 phases coexist at the same time, you have to go down to a very weird or very low pressure to satisfy that condition. Typically, it's hard to achieve that. And more importantly, if you're in this region, for instance, the temperature and pressure is over here. So if your temperature and pressure is over here, then it means that you only have 1 phase, but you have 2 degrees of freedom, right? Because you can change temperature, you can change pressure, but you are still within this boundary. You are still in the liquid phase. If you want to stay on this line, imagine that if you want to stay on this line, it's common sense that you lose 1 degree of freedom, right? Because now pressure is a function of temperature, or temperature is a function of pressure. So you lose 1 degree of freedom. So on the coexistence line, coexistence of 2 phases on this borderline, you only have 1 degree of freedom, right? You can move around, but P and T depends on each other. Therefore, that's the reason why we want to find pressure as a function of temperature. And for the triple point, of course, there's no degree of freedom at all because there's just 1 point, right? So you cannot move around. It's just 1 point. So these are just the things that we've already mentioned. The most important thing is this Gibbs phase rule to describe what I just mentioned using words. The degree of freedom is represented by F over here equals to the number of components minus the number of phases plus 2. The 2 over here is the original degree of freedom, which is temperature and pressure. Right? We haven't discussed about, let's say, the chemical potential yet, right? Like I mentioned at the beginning of this week, of today, that we're going to ignore the chemical potential for this chapter because right now we're dealing with just 1 component system. So here, the number of components is actually the number of components here because we only have 1. So in the case of water, we have F is C plus what? Plus 2 minus phi. And for the case of water, the component is 1, right? You only have 1 component, which is water. And we have plus 2. This corresponds to temperature and pressure. So originally, if you have no confinement at all, then you have 3 degrees of freedom. You have 3 degrees of freedom. But for instance, if you're dealing with the coexistence of 2 phases, like along this line, then you have to minus 2. So eventually, you only have 1 degree of freedom, for instance. If you're dealing with a triple point, the coexistence of 3 phases, then you have 3 over here. Because phi is 3, you have 3 phases. Then this will become 0, right? You have 0 degrees of freedom because it's just a single point. So Gibbs phase rule is actually just a summary of what, based on the observation on the phase diagram. This seems to be pretty simple in the 1 component case. But if you're dealing with, for instance, alloys or mixture of different kinds of materials, and this phase rule might be useful for you to determine like how many degrees of freedom that you have and what kind of variables that you want to fix in order to discuss just some certain degrees of freedom. Okay, but at this point, at least in this semester, this is not a very useful expression. But this is a rule that typically, if you're going through phase diagram, typically they will ask you to learn this. So here it is. So if you look at, if we go back to the plot of Gibbs free energy again, actually they have different kinds of trends at the different parts on this phase diagram. So I don't want to plot this again on Blackboard. So I think this is also shown in your textbook. So it should be pretty straightforward if you already know what I just went through earlier today. For instance, at the very beginning when we're talking about the regular condition, which is 1 atmospheric pressure, if you're cut along this line, we fix the pressure at 1 atm. And if you cut along this line, we've already mentioned this cross-section from A to B, for instance, from A to B. And this is what you will get. You have the solid, you have the liquid. Anyways, let's plot this again over here. Things are very straightforward. So again, we're using this phase diagram, and we have solid, liquid, but now including the vapor phase or gas. So I use these two terms interchangeably. If your line is cut over here, this is constant pressure, and so P is fixed at 1 atmospheric pressure. And if you plot the Gibbs free energy as a function of temperature, just like this, like as a function of temperature, you just go from here to here, right? And of course, we know that originally a solid should have the lowest Gibbs free energy. So maybe you have a solid like this. And then maybe I should make this more flat. Solid. And then at a certain point, you have the liquid phase being the lowest Gibbs free energy. So maybe something like this. So this is solid, this line. This is liquid. And we've already seen this before. And we know that, first of all, let's review that the slope should be negative, and the curvature should also be negative. So it's bending downward. But now we also have this transformation from liquid to vapor, and it should be going downward like this. And we know that this point is the melting point. This is Tm. Or for water, this is 0 degrees Celsius, or 273 Kelvin. And this corresponds to a little bit off here, right? And this point corresponds to the boiling point of water. So it should correspond to this point. Let's make this simpler. Remove these things. Okay. So if it is beyond the boiling point, we know that the vapor or the gas phase should have the lowest Gibbs free energy because it's becoming stable. But if you're on the boundary, if you're right on the spot, here and here, then the Gibbs free energy should be the same. Okay, so that's the idea that is modified from what we learned earlier. And of course, at a triple point, you'll see a different condition, that all three lines are converged onto the same point. They intersect onto the same point. So that's the case when it's the only case when you have three lines crossing each other. So that's the triple point. Of course, if you deviate from triple point, you have a different scenario. So the bottom line is that when you change the pressure, and if you plot Gibbs free energy as a function of temperature, you'll see those lines like changing and moving upward or moving downward. But they all can describe what you see on the phase diagram. Okay? And this is the simplest case, as we're dealing with, since we're dealing with just one component, and it's water. And also, you have to understand that the entropy of solid is less than the entropy of liquid, and it's less than that for vapor. So that's the reason why the slope here is, this is more mild, this is becoming more and more, I won't say aggressive, but it's more and more sharp. So the slope is becoming, the magnitude of the slope is becoming greater and greater, right? Because, again, the partial G, partial T, and the fixed pressure is minus S. So if you're dealing with the slope, the magnitude of the slope is simply S, right? So imagine that if you're dealing with a liquid phase, the slope should be greater in terms of magnitude, greater than that for the solid phase, and the vapor should be much bigger. So you'll see that the slope is becoming greater and greater in terms of negative values. Okay. But for people dealing with metals, or eventually if you want to study metals or metallurgy, of course, you will be dealing with solid-solid equilibrium. And there are several different kinds of, I would say, metallic phases. For instance, if you're dealing with just single atoms, for instance, let's say tantalum. Typically, when we talk about tantalum, it's probably you'll have different kind of phases like amorphous, crystalline. Even for crystalline phase, you could probably have like BCC or FCC structures, depending on the pressure and the temperature of your system. So if you're dealing with single elements, you still can have different kinds of crystal forms. So allotropy means that you have elements that can exist in more than one crystal form. At least in my personal research, I work on, for instance, heavy metals for spintronics applications. And one of them is, one of the most interesting material is tungsten. And tungsten is a very common metal. You know that Edison used that for generate the, the light using electricity. And so it's a very, very common metal. And in fact, it has different kinds of forms. It has beta phase and it has alpha phase. So even for tungsten, you have alpha phase and you have beta phase. And alpha tungsten is BCC, and beta tungsten is having this kind of A15 cubic structure. You don't have to memorize this, but just an example that even for tungsten, it can have like different kinds of microstructure. And by changing the temperature or the pressure, you can change this from one phase to a different phase. So this is a solid to solid phase transformation. And if we're dealing with chemical compounds, it's called polymorphisms. It's just different kinds of naming. But all these, both of these are trying to describe solid to solid phase transformation. So for instance, if you're dealing with, let's say, phase change memory, it has a GST, which is germanium, selenium. Is selenium or antimony? I couldn't remember. Maybe it's just, or maybe just 2.5, this is 5. So let's say this is with some certain fractions. So this is a chemical compound. And this is a material that can transform from, say, amorphous to crystalline. So this kind of compound is not a single element. It's a kind of chemical compound. You can have this from a liquid-like amorphous form and can change that into crystalline form. So if you want to look into that, this is the physics behind, this is the material behind the so-called phase change memory. You can use electricity to heat up the sample, heat up your material, and then change the resistance, change the crystal form, therefore change the resistance. So this is an example of a polymorphism that's mentioned in the textbook. So, but the bottom line is that if you consider just solid to solid transformation, we typically will go back to the original Clapeyron equation because we're no longer, we're not allowed to use that approximation. So you'll recall this original equation, this is what you will get. And typically, if you want to figure out the slope, again, you use this original equation. So if you can figure out delta H and if you can figure out delta V, you should be able to predict, again, the slope of dP over dt. And in this case, the textbook shows the example of iron. Okay, and for iron, the slope for alpha to gamma phase transition is actually having a negative slope, while that for gamma to delta and delta to liquid phase transformation is having positive slopes. So these are, for instance, these are the triple points that three phases can coexist, and these are the borderlines that we've been discussing. So, I mean, this is just an example of what you can predict by measuring, for instance, a molar volume change for solid to solid phase transformation. So next time we'll come back, finish this, and then just talk about some numerical examples, and we'll finish chapter 7.